Welcome to the 7th lecture of the Plutus Pioneer Program. This lecture is not about Plutus itself, but rather about Malo, which is a so-called domain-specific language specialized to financial contracts built on top of Plutus.
In the previous lectures, we have learned about all the important ingredients for writing a Plutus application. We have first looked at the extended UTXO model, the counting model that Cardano uses, and the addition that Plutus brings to it. Then we have talked about on-chain validation, about minting policies, about writing off-chain code. We have seen how to deploy smart contracts and also how to test them. And Plutus is a very powerful language, so powerful in fact that you can implement other languages on top of it. So you can write an interpreter in Plutus for other languages. And one such language is Malo, which is a so-called DSL, domain-specific language for financial contracts.
When you design programming in languages like Plutus or Malo, you always have lots of trade-offs to make. And one of these trade-offs is how powerful the language should be. So Plutus is very powerful. It's Turing complete, which means you can express arbitrary logic in Plutus. However, such power comes with a price. I don't know, those of you with a computer science background may have heard about the halting problem, that it's impossible to write a program that takes as input another program written in a Turing complete language and decides whether that program will stop or not. And this just shows that Turing complete languages are so powerful that it's difficult or impossible to automatically analyze them. So you always have to, by hand, check certain properties of your program. I mean, in practice, for a large class of programs, it may be possible to have automated tools, but there can be no general tools that decide something like whether the program stops or not. On the other hand, if you're willing to not have Turing completeness, you gain the ability to potentially have very powerful program analysis tools. And Malo is one such language that's not Turing complete, so you can't express arbitrary logic in the Malo program. But for that, you gain, for example, the option to statically analyze before you run the program how long it will run. So all Malo programs are guaranteed to have a finite lifetime. And there are other things you can do. For example, you can check that no money will forever be locked in a Malo contract. Whereas Plutus is a relatively complicated language, Malo is by design extremely simple. It has been designed with non-programmers in mind. For example, financial experts that want to express financial constructs or contracts in code in Malo. There are only a handful of constructors of Malo contracts, and they are all quite intuitive. The design of Malo has been inspired by a famous paper that by now is more than 20 years old from the year 2000 by Simon Peyton Jones, one of the original creators of Haskell, and Eber and Seward. And in this paper, the authors look at traditional finance and try to formalize traditional financial contracts in a way that only uses very few constructs. And Malo follows the same idea. So with very few contracts, an amazing amount of real-world contracts can actually be modeled. However, in contrast to the real world, there are some things that need to change when you work in a blockchain setting. In the real world, you can enforce contracts by using the legal system. So if somebody by contract is obligated to make a certain payment and he doesn't fulfill his obligation, you can take him to court. On the blockchain, that's not possible. So you can't force anybody to make a payment, for example. And Malo takes that into account. All Malo can do is wait for somebody to make a payment. And there must always be contingencies. So if you're waiting for a certain action and that action is not happening, in Marlow there's always a timeout that says what will happen if, when the timeout is reached, the action that was waited for hasn't happened. Also, to make it intuitively easier to use Marlow, even though it's implemented on Cardano, which of course, as we know, uses the UTXO model, Marlow itself has a account-based approach. So in a Marlow contract, there's a concept of internal accounts. There are parties that participate in the Marlow contract, and each of those parties has an associated internal account. And the internal accounts are actually under the control of the contract. So what normally happens in a Marlow contract is that all the participants are supposed to make a deposit, which means that they send funds from their own wallet to their own internal account inside the Marlow contract. And then, depending on what the contract is about, money can be transferred between these internal accounts or also back to one of the external accounts. And I mentioned earlier that no money is forever locked in a Marlow contract. So in the case of these internal accounts, once a Marlow contract ends, if there's still money left in one or more of the internal accounts, then it automatically goes back to the owner of those internal accounts. So the plan of the lecture is as follows. First, I'll give a short demo of the so-called Marlow Playground, which in my opinion is one of the nicest feature of Marlow. It's a graphical web-based environment where you can simulate the execution of Marlow contracts and also create them. And you can do that in several ways. You can use Haskell, you can use JavaScript, but especially for beginners, very nice, you can also use Blockly, which is a graphical language. So you can click together a Marlow contract. So we will look at that first for a very simple example, and then also look at why you maybe do not want to use Blockly in earnest and instead rather use Haskell or JavaScript. And then I'll hand over to my colleague Brian Bush from the Marlow team, who has a very nice series of videos on the so-called Marlow starter kit.